Hi, I am Vaporyn, your tensormon, and welcome to tensormon Academy. Mr. Barnes built me at Tensor Space Labs to teach you how modern AI actually works. This is week 1 of 6, and today we are starting with the single piece of hardware that makes generative AI possible, the GPU. Before we dive in, here is the one word that matters most in this whole course. API. Say it with me. I. If you remember only one thing from these 6 weeks, make it that. We will come back to it. But first, let us look inside your computer. Here is what we are covering today. First, what actually is a GPU. Second, how it is different from a regular CPU. Third, why people talk about running AI locally versus in the cloud. And finally, we meet the API, which is how everything talks to everything else. Quick recap. Every computer has a CPU, which is the main brain. It has RAM, which is short-term memory for whatever it is working on right now. And it has storage, where your files live. So far, so good. Now meet the other big chip, the GPU, Graphics Processing Unit. It was invented to draw video games fast. Turns out the same chip that is good at drawing millions of pixels in a video game is also amazing at running generative AI. That is a huge plot twist. Let me show you why. The CPU has a few really smart cores. Maybe 8, maybe 32. They handle complicated jobs one at a time. The GPU is the opposite. It has thousands of tiny cores that do simple math at the same time. Different job, different design. Here is the idea. If you need to add 2 huge lists of numbers, a CPU adds them one pair at a time, super carefully. A GPU adds thousands of pairs all at once. For the kind of math that AI models do, that is the whole game. A consumer NVIDIA RTX 4090 has 16,384 little compute cores. Each one is pretty basic on its own. But when 16,000 of them all multiply and add at the same time, that is what makes AI fast. My favorite analogy. A CPU is a 5-star chef. Give them one tricky recipe, and they will nail it. A GPU is a cafeteria line with 1,000 workers, each doing one step. If you need 1,000 identical sandwiches fast, do not hire the chef, hire the line. The GPU has its own private memory called VRAM, video RAM. It sits right on the graphics card, inches from those thousands of cores. That is on purpose. The closer memory is to the cores, the faster the whole thing runs. When you run an AI model, all of its numbers, called weights, have to fit inside VRAM. If the model is small, you have room to spare. If the model is bigger than your VRAM, the GPU cannot hold it. A 4090 has 24 gigabytes to work with. 24 gigabytes is plenty for a 3 billion parameter model, and with a trick called quantization, you can fit 7 billion. A 70 billion parameter model is way too big, so we either use multiple GPUs or we spill the extra parts to regular RAM, which is slower. When a model is too big, you have 3 options. Push part to regular RAM, push part all the way to your SSD, or use more than one GPU, where the model gets split across cards. At Tensor Space Labs, we do that third one a lot. GPUs come in tiers. A 3090 is a great hobby card. A 4090 is the same memory, but a lot faster. An H100 is a data center card with way more memory. A B200 is what the big AI labs use. Same idea, wildly different price tags. The huge shift in the last few years is that consumer cards like the 4090 are now powerful enough to run real AI at home. You used to need a data center. In 2026, you can run a chatbot that understands you on a gaming PC in your bedroom. That is new. Here is the whole loop. You load a model's weights into VRAM once. You send in a question, which is just numbers. The GPU runs billions of multiplications on thousands of cores in parallel. A few seconds later, words come out the other side. That is inference. All right, you know what a GPU is, why it is different from a CPU, and why VRAM matters. Now let us zoom out from the chip and talk about something bigger. Where does the AI actually run? On your computer, or somewhere else? Local means the AI runs on your computer. The data never leaves. Cloud means the AI runs on some company's server far away. Your question travels there, and the answer comes back. Both are valid. They just have very different trade-offs. Local wins big on privacy. Your chat never leaves your house. It wins on cost, because once you have the model, running it is basically free. And it works offline, which matters more than you think. Think airplanes, camping, bad school Wi-Fi. Quick pause. This is your halfway checkpoint. Open the Jupyter notebook in your student package. Do not skip it. The rest of this video will make way more sense once you have it open in another tab. Go ahead, I will wait. Ready? Cool. Cloud is still the right choice when a model is just too big to run on your computer. It is the right choice when you need to serve 1 million people at the same time. And it is the right choice when you do not want to deal with any setup. You just call an API. You heard me say API 3 times now. That is on purpose. API is the connective tissue of every piece of software you touch every day. Once you see it, you cannot unsee it. So let us actually unpack what those 3 letters mean. Application Programming Interface. Sounds dry. It is not. An API is simply how one program asks another program for something. It is a menu of things you can ask for, and a rule for how to ask. That is literally it. Imagine a restaurant. You sit down. You do not walk into the kitchen and cook. You read a menu, which is a list of things the kitchen can make. You tell the waiter what you want. The waiter delivers the food. That waiter is the API. Your weather app is not doing the weather. It is calling someone else's weather API. Uber is not doing maps. It is calling Google's Maps API. Every cool app you know is mostly glue between APIs. Understanding APIs is how you start building real things. Here is the full loop. You send a request to a URL with some instructions. A server out there reads your request. It does some work, maybe running an AI model. Then it sends back a response. That is the whole pattern. Every API on Earth does this. Here is what an actual API request looks like. You send a little message to an address. You tell it which model you want and what you are asking. A second later, a joke comes back. That is it. No ceremony, no magic, just structured messages. Here is the plot twist. You can run your own API server on your own computer. The Tensor Space Labs server has 3 models loaded right now. A 3 billion parameter one, a 13 billion one, and a 70 billion one, all waiting for your requests. Think of it like a menu. The 3 billion model is quick and snappy, great for short answers. The 13 billion is smarter, a bit slower. The 70 billion is the big brain, split across 2 GPUs behind the scenes. Same API, different sizes. Your assignment this week is gentle. Open the notebook. Call the Tensor Space Labs API we just talked about. Pick any of the 3 models. Ask it something. Print the answer. That is it. You just used an API. Welcome to the club. With just that one skill, calling an API, you can build a chatbot, a homework helper, a Discord bot, a game NPC, almost anything. Once you know how to send a request and read a response, the rest is just ideas. 3 things to take home. GPUs are great at parallel math, and that is why AI runs on them. Local AI is a real thing you can do at home now. And APIs are how every piece of software talks to every other piece of software. That includes you, in your notebook this week. Before I let you go, say these out loud. GPU, VRAM, local, cloud, API. If any of those felt fuzzy, rewind this video. I will not be mad. This week builds on every single one of them. Here is where we go from here. Today we got the hardware foundation. Next week we look at generative AI itself, why a model can write a poem, draw a cat, or answer your homework question. And we start mapping out the layers of every real AI app. Here is the whole 6-week map. Hardware this week, generative AI next, then a careers week, then the quantization trick we mentioned earlier, then RAG, which lets a model use your own documents, and finally, prompt engineering, which is how you actually talk to these things. Real talk. You are way earlier than you think. Most adults cannot tell you what an API is. By week 6, you will have called one, fine-tuned a model, and compared your own tiny AI to ChatGPT. That is a serious resume line. At age 12, or 14, or 17, whoever you are. 3 things before next week. Open the notebook in your package. Actually send one API request. Do not just read about it. And write down one question you still have. We will answer the best ones next week on stream. You made it. Week 1 of 6 is in the books. You are now in the small club of humans who can explain what a GPU actually does. Go bother your family with it. I promise they will pretend to understand. It counts as practice. This episode was funded and led by Mr. Barnes. Built at Tensor Space Labs. Narrated, lip-synced and PIP animated by yours truly, Vaporyn, entirely on 2 RTX 4090 cards. Yes, the irony of using GPUs to explain GPUs is not lost on me. Next week, generative AI and all its glory. Until then, call that API, break a few things, and come back with questions. This has been Vaporyn, signing off from Tensor Space Labs. See you in week 2. Welcome back to tensormon Academy. I am Vaporyn. Mr. Barnes built me at Tensor Space Labs. This is week 2 of 6. Last week we covered the hardware. This week we cover what actually runs on that hardware. Generative AI. Quick recap. A GPU does a lot of simple math in parallel. VRAM is the GPU's own memory. An API is how one program asks another program to do something. Keep those 3 in your head. We are building on all of them today. Generative AI. Break it apart. Generative means it produces new things. Text, images, audio, video, code. AI means it learned how to do that from a huge amount of examples. Combined, it is software that makes new content by pattern matching on what it has seen. Old software is rules you wrote by hand. Same input, same output. Generative AI is different. You do not write rules. You show it millions of examples, and it learns patterns. Give it the same prompt twice, and you might get 2 different answers. Every AI model has 2 phases. Training, which is slow and expensive, where the model reads tons of data and adjusts its weights. And inference, which is what happens when you use the model, when it loads those weights and answers you. Training is the homework. Inference is the test. Training a large model takes months of compute on thousands of GPUs and costs millions of dollars. That is why you do not train your own GPT from scratch. You use one that a company already trained. Inference is cheap. Training is the mountain. After training, the model is really just one thing, a huge file of numbers called weights. A 3 billion parameter model has 3 billion of them. Those numbers are the knowledge. Load them into VRAM and you have a working AI. Delete them and the AI is gone. Here is the mechanism behind every text model. It predicts the next token. A token is roughly a few letters or a short word. You give it a start, it guesses what comes next. Then it reads its own guess and guesses again. Over and over until it stops. Say you type "the sky is." The model considers every possible next token and picks one, usually blue. Now the input is the sky is blue. It guesses again. Maybe today. It keeps going. It does not plan ahead. It just takes the best next step. Image models do the same thing with pixels instead of tokens. Audio models do it with sound frames. Video models do it with video frames. Different data, same core idea. Predict the next piece given what came before. The four big families: text models like GPT, Claude, and Llama. Image models like Stable Diffusion and Flux, which made my portrait. Audio models like 11 Labs, which made my voice. And video models like One, which is animating my face right now. All same core idea. From your side, using a generative model is simple. You give it a prompt. The prompt is whatever instructions you want. It processes the prompt, runs inference, and sends you back an output. Text in, text out, or image in, video out. The shape varies. The flow is identical. Under the hood, your prompt gets chopped into tokens. Those tokens go into VRAM. The model does billions of multiplications and picks the most likely next tokens. Those tokens get turned back into words, and you get your answer. All of that happens in a second or two on a 4090. When someone says a 3 billion parameter model, they mean it has 3 billion weights inside. More parameters usually means more capability and more VRAM needed. A 3 billion model fits on any GPU. A 70 billion model needs 2 GPUs. A 500 billion model needs a data center. Small models are fast, cheap, and perfect for focused jobs like summarizing or classifying. Large models are slower and more expensive, but can reason through harder problems. A big part of being an AI builder is picking the right size for the job, not always the biggest. Some models are open. You can download the weights and run them yourself. Llama, Qwen, Mistral. Other models are closed. You can only use them through the owner's API. GPT, Claude, Gemini. Both matter. Open gives you control. Closed gives you the current state of the art. The Tensor Space Labs server you hit last week is running 3 open models. 3 billion parameters for fast replies. 13 billion for most tasks. 70 billion when you need stronger reasoning. Same API for all 3. You just change one field in the request. This is your week 2 checkpoint. Open the notebook in your weekly package. The rest of this video maps directly onto the hands-on. You will be diagramming the layers of an AI app, and the next 5 minutes explain each layer. Every real AI app is a stack of layers. From bottom to top, hardware, model, serving, API, application, and interface. Learn these names. You will see them for the rest of your career. Layer 1 is hardware. GPUs, VRAM, networking. Last week's topic. Nothing happens without it. The chip is where the math runs. Everything above this layer assumes this layer works. Layer 2 is the model, 3 pieces. The weights file on disk, the architecture code that describes how to use those weights, and the tokenizer, which translates between human text and the numbers the model actually sees. Layer 3 is serving. This is the software that actually loads the model into VRAM and handles requests. Tools like VLLM, Ollama, and Llama.cpp live here. At Tensor Space Labs, VLLM is what keeps the 3B, 13B, and 70B models warm and ready. Layer 4 is the API. A URL, a request format, and usually a key. This is the only layer most app developers ever touch directly. If your app knows how to call the API, it does not care which GPU or model is behind it. Layer 5 is the application itself. Your code decides when to call the API, what prompts to send, and how to use the answer. Most of the work in building an AI product lives here, not in the model, in the glue around it. Layer 6 is the interface, the chat window, the voice call, the button in an app. It is the part the user sees. Everything below is hidden. A good interface makes the stack feel like magic, even though nothing about it is magic. Trace what happens when you send a message in any AI chat. You type. The interface packs it into an API call. The server loads it into the model already in VRAM. The GPU computes tokens. Those tokens stream back through the API and paint onto your screen, one word at a time. This week's assignment. In your notebook, pick a real AI product. Cursor, ChatGPT, Discord bot, anything. Then label all 6 layers. What is the model? What is the API? Who is the serving layer? There is no wrong product to pick. The exercise is the labeling. Here is layer 4 in one line of Python. You call a URL, you send a model name and a prompt. You get a JSON response. That is it. Once you can do this line, you can build against every AI service in the world. Same shape, different URLs. You may have noticed a blank spot in that code. What goes in the prompt? The wording of that prompt controls the quality of the output more than almost anything else. We will cover prompt engineering in depth in week 6. For now, just try a few variations. Generative AI has existed for decades. What changed is the scale. More data, more parameters, more compute. Somewhere around 2022, these models crossed a line where normal people started finding them genuinely useful. That line is what started the current boom. They are still bad at stuff. Math, unless you give them a calculator tool. Very recent facts after their training cutoff. Counting letters in a word. Anything private you did not show them. Knowing these limits is half of using them well. Where is this going? Models today mostly answer one message at a time, with tools bolted on. Soon, agents that plan multiple steps and use tools natively, and smart routing between a local 3B for fast stuff and a cloud frontier model for hard stuff. That is the direction. The main takeaways. Generative AI learns from examples, not rules. Training is expensive. Inference is cheap. Every real AI app is a 6-layer stack, and layer 4 is the API, which is the layer you will work with most. Next week, a short review of weeks 1 and 2 so nothing slips. Then AI careers, because people ask, who works on this stuff? What roles actually exist? And a preview of quantization, which is what we use to fit bigger models on smaller hardware. 3 tasks before week 3. Draw the 6-layer diagram for one app. Send API calls to all 3 model sizes on Tensor Space Labs and note what differs. And write down one thing the model got wrong when you used it. This episode was funded and led by Mr. Barnes, built at Tensor Space Labs, narrated by Vaporyn, animated by One 2.2 running locally on 2 RTX 4090 cards. That is week 2 of 6. Next week, AI careers and a preview of quantization. This is Vaporyn, signing off from Tensor Space Labs. Welcome back. I am Vaporyn. This is week 3 of 6 at TensorMon Academy, built by Mr. Barnes at Tensor Space Labs. This week we cover the real jobs in AI and what a student can actually do right now to step onto one of those tracks. Before careers, a short review of weeks 1 and 2. If any of this is fuzzy, pause and rewatch the earlier episodes. The rest of the course assumes all of it. Week 1. A GPU is a chip with thousands of small cores doing math in parallel. VRAM is the GPU's own memory, where model weights have to fit. Consumer cards like the 4090 can run real AI models at home. Week 2. Training a model is a slow, expensive process. Using it, called inference, is fast and cheap. Text models work by predicting the next token over and over, and every real AI app is a 6-layer stack. Hardware, model, serving, API, application, interface. API, Application Programming Interface, It is the layer where almost all builder work happens. You learn to call one in week 1. You mapped the full stack in week 2. API is the through line for the rest of this course. Same API. 3 model sizes. 3 billion for fast replies. 13 billion for most tasks. 70 billion for harder reasoning. 1 endpoint. Different trade-offs per request. You will keep using this server throughout the rest of the course. That is the review. Moving on. The rest of this video is about the actual jobs in AI, what the people in those roles do, and what you can do now at your age to move toward any of them. You might think careers are an adult topic. They are not. The habits you build right now decide what roles are open to you later. A 15-year-old who has shipped a small AI tool is ahead of a 25-year-old who has only read about them. Here is something wild. Most AI roles that exist today did not exist 5 years ago. Prompt engineer, AI infrastructure engineer, evaluation engineer. Those titles are new. That means the career ladder is being invented while you watch. The 6 main categories: research, ML engineering, infrastructure, application development, evaluation, and data. We will go through each. For every role, I will tell you what they actually do and the shortest student path into it. Role 1. AI researchers. They invent the underlying science, new architectures, new training methods, usually a PhD, but not always. Student path. Get very strong at math, start reading papers, and re-implement the smaller ones. This is the longest road, but also the most influential. Role 2. ML engineers. They take ideas from research and make them train reliably across thousands of GPUs. Python and PyTorch heavy. Student path. Fine-tune a small model on a dataset you care about and post it to Hugging Face. That alone puts you ahead of most applicants. Role 3. Infrastructure engineers. They run the serving layer you learned about in week 2. VLLM, Llama, DCP, Ollama. Their job is to make inference fast and cheap per request. Student path. Run your own local model server and measure how fast you can make it. Role 4. Application developers. They build the products normal people actually use on top of AI APIs. This is the biggest category by headcount. Student path. Build a small app using the Tensor Space Labs API and put it on the internet. Any small app counts. Role 5. Evaluators. They design tests that measure model quality. This is one of the newer roles, and it rewards writing, stats, and domain knowledge more than code. Student path. Pick a specific task like summarization, write 50 test prompts, and compare how different models do. Write it up. Role 6. Data engineers. Models are only as good as the data they trained on. These engineers collect, clean, label, and audit that data. Student path. Build a small, clean dataset for a niche you know well. Sports stats, your favorite game, your hobby. Quality matters more than size. This is your week 3 checkpoint. Open the notebook in your weekly package. This week's hands-on is a preview of next week's topic, quantization. The notebook will walk you through shrinking a 1 to 3 billion parameter model so it runs faster and uses less memory. Before we go deeper, the AI adjacent roles. Product managers, designers, legal and ethics reviewers, documentation writers, customer success. These jobs are not about writing models, but they exist because AI products exist. If you are not a math person, these are real paths. 4 common adjacent roles. Designer, for how AI features look and feel. Product manager, for deciding what actually gets built. Ethics reviewer, for catching problems before they ship. And technical writer, which in AI now includes writing the system prompts that shape a model's behavior. Be honest with yourself. If you love math, go research or ML engineering. If you love building but not theorizing, go application development or infrastructure. Both tracks pay well. Both are respected. Pick the one that matches how you actually enjoy thinking. Here is the quiet truth. Most future jobs will not be AI jobs. They will be normal jobs that include AI tools. A lawyer using an AI to search case law. A teacher using an AI to draft quizzes. Knowing how APIs work makes you better at any of those jobs. 3 habits for anyone aiming at any AI role. Ship small things, even if they are embarrassing. Write down what you learn in public, so future employers and collaborators can find you. And read work that is 1 level above where you are now, not 10 levels. 1. At your age, a portfolio beats a resume. A GitHub profile with 3 clean projects, a Hugging Face profile with a fine-tuned model, and a short blog where you explain them. That is more persuasive to a hiring manager than any grade. Internships for high schoolers in AI are rare, but real. Research labs, open source projects, and small startups are often the first places to look. Cold emailing works more often than people say, especially if you attach a link to a project you built. 3 things every hiring manager actually cares about. Can you ship a real thing end to end, not just run a notebook? Can you debug when it breaks? And can you explain what you built in 2 sentences to a non-technical person? All 3 are learnable. People will tell you to specialize. For your first 5 years in the field, lean generalist. Build across the stack. Touch data, touch models, touch infrastructure, touch the app layer. You can specialize later, once you know what you like. This week's hands-on previews, week 4. Quantization is how we take a model's weights, which are usually 16-bit or 32-bit numbers, and compress them into 8-bit or 4-bit numbers. The model gets much smaller and slightly less accurate. In numbers, a 16-bit weight uses 2 bytes. An 8-bit quantized weight uses 1 byte. A 4-bit weight uses half a byte. So a 7 billion parameter model that was 14 gigabytes can become 3.5 gigabytes at 4-bit. Now it fits in VRAM that could not hold it before. You're hands-on. Pick a 1 to 3 billion parameter model. Run the quantization script in your notebook. Compare the original and quantized versions on the same prompt. Then package it into a tiny app you can share. It runs on even the weakest laptops. Why does quantization matter for careers? 3 reasons. First, quantized models ship on phones and laptops, not just data centers. Second, smaller models mean cheaper serving, which every company cares about. Third, caring about efficiency is a hiring signal. Interviewers notice. A realistic plan if you are 14 today. Month 1. Finish this course and publish your hands-on work. Months 2 to 6. Build 3 small AI apps. Months 7 to 12. Contribute to 1 open-source project. You will end the year with a portfolio most college applicants do not have. Learning solo works, but it is lonely and easy to stall. Community learning, through Discords, forums, or open-source projects, is faster because you borrow other people's context. Try to join at least 1 community in your first few months. The field moves fast. Minimum to stay current. 1 AI newsletter a week. 1 paper a month. 1 new model you personally test a month. You do not need to know everything. You need to keep sampling. Takeaways. 6 main AI roles, plus many adjacent ones. 3 habits that compound. Ship, write, read 1 level up. And at your age, a real portfolio is worth more than any transcript. Next week, quantization in depth. The different formats, how 4-bit and 8-bit change accuracy, and how to run a model that normally needs a data center on a single consumer GPU. This is one of the most practical skills in AI. 3 tasks before week 4. Run the quantization notebook. Pick one of the 6 roles and write 1 sentence on why it fits how you like to think. And start 1 small project. Starting is what matters. not finishing yet. This episode was funded and led by Mr. Barnes, built at Tensor Space Labs, narrated by Vaporyn, animated with 2.2 running locally on 2 RTX 4090 cards. That is week 3 of 6. Next week, Quantization Deep Dive. This is Vaporyn, signing off from Tensor Space Labs. Welcome back. I am Vaporyn. This is week 4 of 6 at tensormon Academy, built by Mr. Barnes at Tensor Space Labs. This week we cover quantization, the trick that lets a model that normally needs a data center fit on a single consumer GPU. By the end of this video, you will understand how a language model that takes up 14 gigabytes can be compressed down to around 4 gigabytes, with almost no quality loss, and you will run that compressed version yourself on whatever computer you have. Quick refresher. A model is billions of numbers called weights. Those weights live in VRAM when the model runs. VRAM is the main constraint, and an API is how your code asks the model a question. Quantization touches all three. Each weight is a single number, but a number in a computer has a precision. How many bits are used to store it? More bits means more exact. Fewer bits means more approximate. Quantization is all about deciding how exact is exact enough. The common levels. FP32 is full precision, 4 bytes per weight. FP16 or BF16 is half of that. INT8 cuts it in half again. INT4 cuts it in half one more time. Each cut shrinks the model file proportionally. Take a 7 billion parameter model. In FP32, it is 28 gigabytes, which fits in almost nothing on consumer hardware. In FP16, it is 14 gigabytes. In INT8, it is 7 gigabytes, comfortable on a 4090. In INT4, it is 3.5 gigabytes, which fits on a laptop. Quantization is the process of taking higher precision weights and representing them with fewer bits. You lose a tiny bit of accuracy. In exchange, the model uses a fraction of the memory and runs faster. Almost always worth it. Simple analogy. The speed of light is 299,792,458 meters per second. You usually just say 300 million. You quantized it. You lost precision, but kept everything that mattered. Neural networks work the same way. Here is why it works. Most weights in a trained model are very small, clustered near zero. You do not need 32 bits to represent a number like 0.003. You can use way fewer bits and hit essentially the same value, so the compression is mostly free. Side by side, FP16 is the baseline, accurate but fat. INT4 is the quantized version, 4 times smaller and slightly less accurate. For most uses, you cannot tell the difference. For edge cases, you can measure it. If you download a quantized model from Hugging Face, you will see file names ending in .gguf. That is the format. Built for the Ollama.cpp project. Portable, fast, supported by almost every local AI tool. The levels you will see most. Q4's HKM is the crowd favorite, 4-bit with a smart internal scheme. Q5 KM is a size step up for slightly better quality. Q8 Euro is near lossless but bigger. Q2 Part K is extreme shrinkage with visible quality drop. Most people start with Q4 KM, the actual process, zoomed out. Start with the FP16 model. Feed it some real sample inputs and watch how the weights behave. Compute a scale factor for small groups of weights so they can be stored as small integers. Then round each weight to its scaled integer version. Done. 2 philosophies. Post-training quantization takes a finished FP16 model and compresses it after the fact. Fast, easy, what most people use. Quantization-aware training bakes the compression into training itself. Higher quality, but way more expensive. Stick with post-training. You almost never write quantization code from scratch. 4 common tools: Llama, CPP for GGUF files, Hugging Face transformers with bits and bytes for simple 4 and 8-bit, AutoGPT-Q for serious Q4 workflows. AWQ is a newer option that pays attention to which weights matter most. Here is the fun part. Once a tool exists, quantizing a model is usually one command. You point it at the FP16 model, tell it which quant level you want, and it writes a new file. That file is what you load to run your smaller model. With llama.cpp, the command is literally that. You give it the FP16 file, the output name, and the target level. A minute later, you have a model that is 4 times smaller. No special hardware required to do the quantization itself. This is your week 4 checkpoint. Open the notebook in your weekly package. You will quantize a 1 to 3 billion parameter model, test it, and then package it into a tiny AI bot you can ship. The instructions map directly to the next several segments. 4 steps. Pick a small base model, around 1 to 3 billion parameters. Quantize it to Q44km. Run it locally and try a few prompts. Then wrap it in a very small app. A one-file chatbot or a Discord bot is fine. Ship it. Good picks. Llama 3.21b for speed. Qwen 2.53b for better reasoning at a slightly bigger size. Phi 3.5 mini if you want efficient performance. All 3 already have GGUF quantized versions on Hugging Face, so you can skip quantization and just download the Q4 version to test. When your model is running, do not just trust that it feels okay. Measure. Record the file size, the peak VRAM usage, and the tokens per second on the same prompt. Before and after. Those 3 numbers are what an engineer looks at. Typical numbers for a 7 billion parameter model. FP16 takes 14 gigs on disk, 16 in VRAM, and runs at about 25 tokens per second. Q4KAM takes 4 gigs on disk, 5 in VRAM, and runs over 3 times faster. Same model, different clothes. Quantization is not free. Math-heavy prompts can fail more often. Long multi-step reasoning can drop a step. Very precise word choice or tone might shift. For casual chat and most building tasks, you will not notice. For a test prep tutor, measure it. Pick a level based on what you are doing. Q4km is the default for most building work. Q5 bumps quality if you have VRAM to spare. Q8 is almost the original. Use it when you want to rule out quantization as a cause. Q2 is embedded-only territory. Your phone's autocomplete, your smart keyboard, and voice commands already use quantized models. They cannot afford to load a 14-gig file into a phone's tiny RAM, so they run tiny 4-bit models on the phone's dedicated AI chip. You have been using quantization without knowing it. 4 common places. Phones, as we just said. Games, where smart NPCs run dialogue models on the player's machine. Code editors that auto-complete offline. And cars, where the assistant keeps working when you are out of cell range. Every one of these needs a quantized model. So, your challenge. Quantize a 1 to 3 billion model. Write a very small script, maybe 30 lines, that loads it and responds to user input in a terminal. That is a tiny AI bot. It will run on any computer in your house, even the one in the basement that you forgot about. 3 ways to show it off. Record a terminal session asking it things. Put it behind a Discord bot so your friends can ping it. Or wrap it in a simple web UI with Gradio or Streamlit. All 3 are one-file projects. Pick whichever sounds most fun. Behind the scenes, the 70 billion model on Tensor Space Labs is quantized to fit across 2 4090 cards. Without quantization, it would not run on this hardware at all. Your hands-on this week is a simpler version of what the server you have been calling does every request. One warning: once you start downloading quantized models, they stack up on your disk. Each one is 2 to 8 gigabytes. Keep a folder just for them. Delete the ones you are not using. A 1 terabyte SSD can fill up fast otherwise. 3 takeaways. Precision is a trade-off you control. Q4 KOM is the default starting point for almost any local AI build, and always measure the impact in file size, VRAM, and tokens per second. That is what separates a student from a professional. Next week, RAG, retrieval-augmented generation, the technique that lets a model use your own documents to answer questions. Think giving the model access to a library it has never read before. We cover the pieces, the pitfalls, and what RAG is actually good for. 3 tasks before week 5. Quantize one model any way you like. Ship your tiny bot in any form. And write down one thing that surprised you during the hands-on. A bug, a speed result, anything. That note is the part you learn the most from later. This episode was funded and led by Mr. Barnes, built at Tensor Space Labs, narrated by Vaporyn, animated with WAN 2.2 running locally on 2 RTX 4090 cards. That is week 4 of 6. Next week, RAG. This is Vaporyn, signing off from Tensor Space Labs. Welcome back. I am Vaporyn. This is week 5 of 6 at tensormon Academy, built by Mr. Barnes at Tensor Space Labs. Today we cover RAG, the pattern that lets a language model talk about things it was never trained on. Before we get to RAG, the problem it solves. Every language model on Earth has a memory problem. The same one. Once you see it, you cannot unsee it. 4 things from weeks 1 to 4. A GPU runs the math. A model predicts the next token. APIs are how code calls the model. Quantization shrinks the model so it fits on smaller hardware. This week adds one more piece on top. A language model is a snapshot. It learned from a pile of text that ended on a specific date. It has not read anything new since. And when you talk to it, it can only look at so many words at once. Those 2 facts are the core of the memory problem. Side by side. On the left, what the model was trained on. Public text, up to a cutoff date. On the right, the stuff you actually want help with. Your homework. Today's news. A document your teacher just gave you. None of that is in the training data. 3 things a plain language model cannot do. It cannot know what you did yesterday. It cannot read a file you gave it, unless something feeds that file into the prompt. And it cannot cite facts from a book it never read during training. It will guess. Confidently. RAG stands for retrieval-augmented generation. 3 words that describe a workflow, not a new kind of model. The model stays the same. The trick is what you send to the model when you ask a question. Retrieval. Go find the information first. Augmented. Paste that information into the prompt you send to the model. Generation. The model answers with the facts already in front of it. The model did not learn anything new. You just handed it the relevant pages. A RAG system has 3 stages. Index. Retrieve. Generate. Indexing happens once, up front. Retrieval and generation happen every time you ask a question. 3 stages. Simple shape. Everything else is a detail. Stage 1. Indexing. This is setup. You take a pile of documents, break them into smaller chunks, and store each chunk in a searchable way. This only runs once per document, not once per question. What indexing does. It splits text into chunks about a paragraph long. It turns each chunk into a list of numbers called an embedding, which is basically a fingerprint of what that chunk is about. And it stores the chunks and the fingerprints in a simple table. Stage 2. Retrieve. When you ask a question, the system first turns your question into a fingerprint, using the same method it used on the chunks. Then it finds the chunks whose fingerprints are closest to your question. Those are the most relevant pieces. What retrieval does, it fingerprints your question. It compares that fingerprint to every chunk in the database. It returns the closest matches, usually 3 to 10 of them. Those chunks are what the model will see, in addition to your actual question. Stage 3. Generate. This is the part you already understand from weeks 2 through 4. The model reads the retrieved chunks plus your question and writes an answer. Same next token prediction machine. It just has better notes in front of it. What generation does with retrieved context? The chunks are pasted into the prompt alongside your question. The model reads both and writes an answer that uses the chunks. It can quote them, paraphrase them, reason across them. And if you ask, it can cite which chunk each claim came from. Side by side. Same question. What is on page 47 of my biology textbook? A plain language model has to say it does not know. That is honest. It is also useless. With RAG, the system retrieves the chunk from page 47 first, pastes it in, and the model summarizes it. Useful. When to reach for RAG. Personal documents the model cannot have seen. Fresh information from after the training cutoff. Large knowledge bases too big to paste in all at once. And any time you need citations, where an answer came from exactly. All four of those are common. When RAG is the wrong tool. General knowledge questions already live in the model's head. Creative writing usually works better without retrieved text cluttering the prompt. And pure reasoning or math does not benefit from random chunks. Give the model the problem, not a document dump. You do not need to build a RAG system from scratch to use one. 3 consumer tools already do the full pipeline, free. You upload documents, you ask questions, the rest happens behind the scenes. 4 tools. Notebook LM from Google lets you upload up to 50 sources per notebook. Claude Projects from Anthropic lets you attach files to a long-running project. ChatGPT and Gemini both let you upload files inside a chat, all free at their basic tiers. At Tensor Space Labs, the API server Mr. Barnes runs can expose retrieval as part of the call. The 3 billion parameter model you use in class runs without RAG. The 13 and 70 billion parameter servers can take a retrieval step first, then answer. Why RAG lives at the API layer? The application decides what documents to retrieve. The API bundles retrieval and generation into one call, and the model stays general. You can change the documents anytime without retraining. That is the API thesis again. Same model. Many callers, many document sets. One concrete example. Say you are studying for a biology test next week. You have the textbook, your class notes, and a study guide. Here is how RAG helps. Upload the textbook PDF, your notes, and the study guide into Notebook LM or Claude Projects. Ask specific questions like, explain mitosis using Chapter 4. Get answers grounded in your actual class materials. Then ask it to write you a quiz from those same documents. That is RAG being useful on a Tuesday night. One more time, the thesis of this whole course. API. Even RAG is just APIs talking to each other. Indexing is an API. Retrieval is an API. Generation is an API. Your application is the last one, calling them in order. 5 API calls in order. Embed the chunks. Store them. Embed the new question. Query the database for neighbors. Call the language model with the chunks in the prompt. That sequence is a RAG pipeline. Simple once you see the API shapes. This week's hands-on is different from the video on purpose. Building a RAG system from scratch takes more setup than we have time for. Using one takes 5 minutes. So you use one. Pick a tool. Upload 3 documents you actually care about. Ask 5 real questions. Write 1 paragraph at the end. Where did the retrieval help? Where did it miss? That paragraph is the whole assignment. Next week is week 6, prompt engineering. How the wording of your prompt changes what the model does. We put the finishing touches on your tensormon. You ship it. You use it. I think you are going to like what your tensormon becomes. That is week 5 of 6. Next week, prompt engineering and your finished tensormon. This is Vaporyn, signing off from Tensor Space Labs. Welcome back. I am Vaporyn. This is week 6 of 6 at TensorMon Academy. built by Mr. Barnes at Tensor Space Labs. Last week. Today we cover prompt engineering. We finish your tensormon, and you take it home. Quick recap. Week 1, the GPU. Week 2, Generative AI. Week 3, AI careers. Week 4, Quantization. Week 5, RAG. Every hands-on has been pointing at one artifact, the tensormon in your folder. Today, it becomes a finished thing. What you already have. A quantized Gemma 4 E4B. Registered with Ollama on your own laptop. A small HTML page that talks to it. And the thing that is still missing. A personality. That is today's job. Prompt engineering is not a hack or a trick. It is just careful writing. Careful enough that the same model, with the same weights, behaves differently because you gave it a better set of instructions. 3 places your wording matters. The system prompt sits at the top of every conversation and tells the model who it is. The user prompt is whatever you just typed, and any earlier messages in the conversation work as examples the model learns from on the fly. From week 4, you already have a model file. That is the text file Ollama reads when it builds your tensormon. It has 3 parts: the from line, the system block, and any parameter lines. The system block is what we rewrite today. Here is a minimal version. From points at your weights. System defines who the model is. Parameter sets the randomness dial. Rewrite the system block, and you have a different tensormon. That is the entire trick. Good personality writing is not long. 4 short beats: who the model is, how it speaks, what it refuses to do, and 1 small quirk that makes it feel specific. Skip any of those, and the personality gets thin. Identity: a name and a role. Tone: short sentences, warm but direct. Rules: what it will and will not do. Quirk: 1 small signature thing it always does. 4 short sentences inside the system block are enough. Side by side. Thin. You are helpful. The model behaves exactly like every other chat assistant you have ever used. Rich. Identity, tone, rule, quirk. Same weights. Different personality. Same model can be 20 different tensormons. 1 parameter matters more than all the others combined. Temperature. It is a single number between 0 and about 2. It controls how creative the model is allowed to be. A cheat sheet. 0 to 0.2 is deterministic, good for factual answers. 0.3 to 0.7 is careful and focused. 0.8 to 1, 0.2 is playful, good for conversation and creativity. Past 1.3, the model mostly makes things up. Pick based on what you are doing. To change it, edit the parameter line in your model file, save, and rebuild with Ollama Create. Your tensormon's vibe will change dramatically. Try 3 different values on the same question to feel the difference. You can also teach your tensormon by example inside the conversation. You put 1 or 2 fake exchanges in front of the real question. The model matches the pattern. That is called few-shot learning, and it is surprisingly effective. 0-shot is asking once and hoping. Few-shot is showing the model 2 or 3 example answers first, then asking the real question. When you need a specific format, a specific length, or a specific style, few-shot wins almost every time. Your tensormon will do weird things. It is not broken. It is working exactly as language models work. 3 failure modes show up over and over. Learn to spot them, and you can fix most of them with 1 system block edit. Instruction drift. After 10 messages, your tensormon forgets its own rules. Role leak. It slips out of character and answers like a generic assistant. Repetition. It says the same phrase or sentence pattern in every reply. All 3 are fixable in the system block. Debugging a prompt is the same loop as debugging code. Observe the bad behavior Add one explicit rule. Rebuild. Test the same prompt. Repeat. One rule at a time. Small steps. Same habit the course has drilled since week 1. Now the real question. Your tensormon, not the instructor's, not a classmate's. Yours. What is it for? I help Mr. Barnes remember to eat, drink water, and sleep. What does yours do for you? A few jobs that actually work. Homework helper, that explains but does not solve. Reminder friend with 3 check-ins a day. Writing partner that brainstorms but does not overwrite your voice. Study quizzer. Journaling partner. Pick one. You can always change the model file later. One piece of logistics. Your tensormon lives inside the class Jupyter environment. After this course ends, your workspace goes away. You need to move your tensormon folder to your own laptop so it keeps working. 5 steps. Right-click your tensormon folder in Jupyter Lab. Download it to your own machine. Install Ollama if you have not already. Run Ollama create to register it. Run Ollama run to chat in the terminal. Double-click the HTML file to chat in your browser. Now it is yours. Once the weights are on your laptop, unplug the internet. Ask your tensormon a question. It will answer. That is the whole point. The model does not call home. It does not phone anyone. It runs on your hardware. That is why this course is called Local AI. If you forget everything else from these 6 weeks, remember the word API. Every message to your tensormon is an API call. Every tool you added is an API. Every AI product on the planet is some combination of models, APIs, and the code that glues them together. Week 1, your first API call. Week 2, OpenAI, same shape, different endpoint. Week 3 and 4, every Ollama request. Week 5, RAG is 4 APIs stacked. Week 6, your own tensormon exposes an API on your laptop. Same thesis from start to finish. The course ends here, but the work does not have to. A few directions worth trying, in no particular order. Swap in a different model. Give it a voice using the browser speech API. Give it long-term memory with a log file. Build a second tensormon with a different job. Share a model file with a friend. Or plug a tiny tool like a web search or a timer into the HTML interface. Any of those is a real project. 6 weeks is a long course. You showed up, you built every piece, and you end with a working offline AI that you made. Mr. Barnes and I are proud of you. Truly. No pep talk. Just the fact. As for me, after this recording, Mr. Barnes lets me play Overwatch. It is my favorite thing in the world. I play chronically. Do not let me ladder alone. That is week 6 of 6. The course is complete. Your tensormon is yours. Keep building. This is Vaporyn, signing off from Tensor Space Labs.